In this problem, we have a solid insulating sphere. It has a uniform charge distribution, and the electric field magnitude at distance d from the surface of the sphere is given. In part A, we'd like to calculate the charge density of the sphere. Let's use Gauss's law. Here's a spherical Gaussian surface that passes through the point at which the electric field magnitude is given. According to Gauss's law, the electric flux passing through this Gaussian surface is equal to the charge enclosed within this Gaussian surface divided by epsilon 0. Because the charge distribution is spherically symmetric and the Gaussian surface has a spherical shape, the electric field vector at any point on the Gaussian surface is perpendicular to the area element at that point. So the electric flux formula reduces to electric field magnitude times the area of the Gaussian surface, which is the area of a sphere. On the other hand, the charge enclosed within the Gaussian sphere can be expressed as the charge distribution of the insulating sphere times the volume of the insulating sphere. We're going to express it that way because the quantity that we're looking for in part A is the charge density. So Q enclosed equals charge density, volume charge density, times the volume of the insulating sphere. By convention, volume charge density is represented by the Greek letter rho, which is what I have here in the equation. Now again, the area on the left-hand side is the surface area of the Gaussian sphere, and the volume on the right-hand side is the volume of the insulating sphere. The area of a spherical surface is equal to 4 pi radius squared, and the volume of a sphere is equal to 4 over 3 pi radius cubed. Next, we substitute the formula for area and volume. Note that the radius of the Gaussian surface is r plus d, that's the radius of the insulating sphere plus distance d, whereas the radius of the insulating sphere is simply r. We have 4 pi on both sides of the equation, so those cancel. And we rearrange our equation to isolate rho, the volume charge density. Next, we plug in the numbers and calculate the final result. Rho is equal to 2.60 times 10 to the negative 7th coulombs per meter cubed. In part B, we're calculating the electric field magnitude at some distance d from the center of the sphere. Now this distance is less than r, so we're calculating the electric field magnitude somewhere inside the sphere. Again, let's apply Gauss's law. Here's the Gaussian surface that we're going to use. The electric flux going through this Gaussian surface is going to be equal to total charge enclosed within the surface divided by epsilon 0. Similar to part A, electric flux is equal to electric field magnitude times the surface area of the Gaussian surface, and Q enclosed is going to be equal to charge density rho times the volume of the Gaussian surface, like so. Now let's substitute the formulas for area and volume. Note that we use d for radius for both the area and the volume because the Gaussian surface now is entirely filled with charge, so there is no gap in between. So we have d on both sides of the equation. Now we have 4 pi on both sides of the equation. Those cancel. And then we have d squared on one side, d cubed on the other side. Those simplify. And then E is isolated, so E equals rho times d divided by 3 times epsilon 0. Let's go ahead and plug in the numbers and calculate. And here's the result. The electric field magnitude at the given distance is equal to 1.96 times 10 to the 3rd Newton per coulomb.